we stopped at discussing the idea of rationalizing. And this was oftentimes, high school algebra teachers love this problem, and I'm not really sure why. When we teach calculus, we say, don't worry about it, that's not that important. But I think mostly they like to teach it because it's about learning to manipulate expressions. And that's what a lot of algebra is. How do you rewrite things? Now, the goal in rationalizing is to basically get rid of those square roots. We don't like square roots, and we can't necessarily get rid of them, but we can move them. So we can move them from the upstairs to the downstairs. That's very rare that we would want to do that. Usually you want to say, let's get them out of the denominators. Okay, so the goal is, let's really try to move square roots. Now, there's a couple things that might happen. What if, let's say, we're in the denominator, and there's no addition going on. It's all products. Like, great, perfect. We like that. And we say, okay, multiply to help get our powers up to whole numbers. And we always multiply by 1, because multiplying by 1 doesn't change the expression. So here, you'll notice in our first example, there is a square root symbol. It's downstairs. And suppose we wanted to get rid of that. Well, there's a couple of ways to go about it, but let's just think about this idea of let's multiply by something to get rid of a square root of 2x. So what can I multiply square root of 2x by so that at the end there's no more square root? Yeah, just multiply it by itself. So multiply top and bottom by square root of 2x. All right, no big surprises. Well, let's see what we get. We get 6x times square root of 2x upstairs, and we can work on that in a second. Square root of 2x times square root of 2x? 2x, our goal. Now, does anything simplify? In particular, think cancellation. Does anything go away? The x's go away. Can anything else simplify?
6 and 2.
Yeah. 6 is divisible by 2. So if we divide the 2 into the 6, that gives us 3 square root of 2x. And that's an answer. Now, the book sort of mentions this implicitly. Sometimes it's not entirely clear exactly what they're after. Because there are many ways to write an expression. Just try to say, do your best to try to interpret what they're asking you for. And as long as you've done what they've asked, like get the square out of the denominator, simplify, do any cancellation, like, okay, then I'm done. All right, now that's if you have products, so that's not too hard. What if addition is involved? Something like maybe a plus or minus b squared of u. This is a very simple case. Not the only way it could happen. So addition makes things more complicated, but not impossible. So we say, all right, we want to get rid of square roots. Now, previously we said, hey, by multiplying that square root by itself, essentially you squared it. And now we start thinking squares. We like squares. And as we dig back into our memories, well, we remember that there's this notion of like a difference of squares. So if you multiply a plus b squared of u times a minus b squared of u, you get a squared minus b squared of u. In other words, you square the first term and you square the second term. And I should have put an a minus plus. So if you have a plus multiplied by a minus, so you have minus multiplied by a plus. This is sometimes called multiplying by the conjugate. Basically says change the sign. But the punchline here is we're getting squares. And we like squares. So, again, we see a square root. There's only one place. So, well, we don't want that square root downstairs. We want to move it upstairs. And there's a minus involved. Okay, so what do you multiply by? So here, we're going to focus on the denominator. So our focus is down here. We're not going to worry about up here yet. Conjugate means change the sign. So what do you multiply by? Square root of x plus 3. Change the sign. Now, you have to multiply by something which doesn't change the expression. So you have to multiply both top and bottom. Because if you multiply both top and bottom, that's multiplying by 1. Now, upstairs, you might say, we got a FOIL. No. Don't FOIL. Don't expand unless you know it's going to help you. Now, downstairs, we know it's going to help us because we rigged the game in our favor. We know it's going to help us, so that's where we should FOIL. Upstairs, because we don't think it's going to help us, don't expand. Sometimes people are too quick to expand. Only do something if it helps you. But downstairs, it will help us, because what's going to happen? Square root of x times square root of x? X. Then we get 3 root x minus 3 root x. All right, the difference of squares, you get cancellation. The oi in FOIL, the o and the I cancel out. Minus 3 times plus 3. Minus 3 times plus 3 gives -9. Okay, now are we done? Or is there anything else that says, hey, I think we can do a little bit more? I think we can do a little bit more here. What can we do? You can cancel the x minus 9s. Now, if you had expanded the upstairs, you wouldn't have seen that cancellation. So that's why I say don't expand unless it's going to help you. So you get square root of x plus 3. Beautiful answer. All right, how about for part C? 2 over square root of 5 minus square root of 3. Now, not just one square root, we're going to double down. 2 square roots involved. So, is there any hope? Can we do it? And if we can, how? Give you a hint, there's a multiplication involved. Another hint, I actually said something, so that means we can do something. Oh, man, that's a pretty strong hint. I'm just like dropping hints here. Yeah, square root of 5 plus square root of 3. Do it upstairs and downstairs. Okay, what's going to happen? Well, let's talk about the downstairs. Square root of 5 times square root of 5. Five. Square root of 5, square root of 3, minus square root of 3, square root of 5. 0. They cancel. That's the point of this difference of squares. The middle terms cancel. Minus square root of 3 times square root of 3? Minus 3. Negative 3. Then there's the 2, and I'm not going to distribute the 2 through. So 2 times square root of 5 plus square root of 3. Okay. Is there anything else that cancels, or are we done? Is there another name, for instance, for 5 minus 3? 2. And we have a 2 upstairs. It's like they rigged the game because they rigged the game. So we get square root of 5 plus square root of 3. Lovely answer. All right, the last one. This one's a little bit more subtle. 1 over 3 plus square root of x plus x. There is a square root. We don't want the square root downstairs. Is there any hope? Any hope? And if there is, how do we go about doing it? So this one is certainly a notch up in difficulty from the rest. Do you think it's possible to get rid of the square root of x downstairs? Now, I'm not saying it's going to necessarily be, there's going to be other stuff that happens. It's not just like, oh, we just erased the square root symbol. I mean, what would you like to be true? You'd kind of like something like in these expressions where you just have like a square root attached to one piece. One thing that makes this hard is how many pieces do we have? 3. Oh my gosh. Whew. But here's the thing. Addition, you're allowed to rearrange. So what we can do is we say, well, let's put the terms in a different order. Why not? So let's put the square root on the end. That's perfectly legal. Totally legal. There's something else about addition. We don't always emphasize this as much as we should. Is that addition, sometimes we can think of it as breaking things apart. We can also think of it as pulling things together. It does both. So what we can do is we can say, hey, let's just think about this thing by 3 plus x as a thing. It's one thing by itself. So now you have a 3 plus x piece and a square root of x piece. Now, given that, what can we do? What should we multiply by? There is something we can multiply by. Well, there will be a 3 plus x. I definitely agree with that. But that by itself won't get rid of the square root. What else do we need? A minus square root of x. So what will happen? Well, upstairs, 1. The good news, 1 times anything is the thing. We've been using that a lot. It's a big thing that happens. Downstairs, you get 3 plus x squared, right? Your first term squared, minus your last term squared, which is x. Now, if you expand 3 plus x quantity squared, that's our 9 plus 6x plus x squared. That's a perfect square. We know how to expand those. And so altogether, we get a 3 plus x minus square root of x upstairs. A plus 6x and a minus x will give us a 5x and plus an x squared. But we did manage to move the square root out. So it is possible. All right, so those are some examples. I would say this one probably a little bit more difficult than what you might see. The first 3 are more typical, the things you could encounter. But it's good to see challenging things. It's good to push ourselves and see how far we can get. All right, one other idea before we move into today's topic, which is scientific notation. And this came about because scientists, in particular physicists, like dealing with numbers, but they discovered quickly that they had sort of 2 extremes. They have things which are sort of size of universe big, and then they have things which are subatomic big. And those are on completely different scales. And so they quickly realized that it was going to be really hard to work with these numbers, especially if you started dealing with interactions on different scales. So they said, okay, let's find a way to express numbers so that we can sort of capture the scale and at least get a better comprehension of the number without being overwhelmed by digits. And the idea was just to say, let's make it look like a smallish number. So we have this coefficient out in front, and it's something between 1 and 10, times the appropriate power of 10. So the appropriate power of 10, we look at this exponent, that gives us the size of the number. It gives us a sense of magnitude. A big exponent in the 10 says you're dealing with a huge number. A small exponent, and by small I mean negative. If you have a sort of a very negative number, that means we're dealing with a very tiny number. So it helps us gather a sense of the scale of the numbers. So for instance, 85,203,000, well, what's happening? We want to take the decimal place, which is currently at the end, and move it over to there. So it would be 8.5203. Now the question is, how far did you move it? Well, we had to move it 7 places. So how far back do we have to go? 7 to the right, that means a plus 7. That's where this 7 came from, is how far did you have to move? On the other hand, 0.0000421, again, we're going to move to where we start, 4.21, but then how far did we move? Well, 1, 2, 3, 4, 5. And if I wanted to get back to my original number, I'd have to move it in the left, so that's why you get 10 to the negative 5. So now, I can say, if I'm really curious mostly about the size of the numbers, if I'm in business and I say, are we talking thousands or are we talking millions? Maybe you don't care, what that leading digit is, but you care about the scale. Then this is the kind of notation that can help. All right, so we'll just do one example here. Use scientific notation to rewrite this expression. Okay, so let's start with the numerator. We say it starts as 9.6, and then everything is 0 after that. So 9.6 times 10. Now the question is, how far did we have to move the decimal? So you start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So what exponent goes up here? To the 9. So 9.6 times 10 to the 9. We're talking billions at this point. Downstairs. Okay, let's look at the next number. Here, we'll start 1.6. Everything else is zeros. And now we start counting. 1, 2, 3, 4, 5, 6. So what do we multiply by? 10 to the 6. Okay. Then we have one more piece that we have to include. This is 0.00025. Okay, so it starts as 2.5. Everything else involved is zeros. And we start counting. 1, 2, 3, 4, 5, 6, 7. What do we have to multiply by? Negative 7, yeah. So the positive and negative sort of helps us understand. So positive, big numbers. Negative exponent means tiny numbers. Now we can take advantage of things that we learned about rules for combining exponents. We can say, well, let's grab those powers of 10 and just put those all together. So if I have 10 to a power divided by 10 to a power and 10 to a power, I can combine them to 10 to a single power. So we have some other pieces times 10. Now, how do we find the new power? What's the procedure? We what?
Subtract the bottom from the top.
Yeah, so things that are upstairs become added. Things that are downstairs get subtracted. So upstairs it was a 9. Downstairs we saw a 6. And downstairs we saw a negative 7. And then we have all those coefficients in the front. 9.6, 1.6, and 2.5. And if we were lucky, this might simplify. 2.5 times 1.6, does that simplify? Well, if you had a calculator, you probably could say, yeah. So for instance, 2 times 1.6 is 3.2. 0.5 times 1.6 is 0.8. And then that means that's all 4. 9.6 divided by 4, does that simplify? Well, yeah, again, this is sort of calculator stuff, not very exciting. It becomes 2.4. 4 times 2.4 is 9%. I'm not expecting you to do these computations in your head. So you have a calculator. But the punchline is the coefficient is 2.4. What power of 10 do we have? 10 to the what? 10 to the 10, right? Because minus minus makes a plus. So you really have 9 plus 7, which is 16, subtract 6. So when you carry out this computation, you get 2.4 times 10 to the 10. And if you wanted to, you could now sit down and figure out how to rewrite this expression. But the point is, it was probably a little bit easier to do this computation than to try to carry out that computation. Because this looks like very discouraging to try to do. All right. So, today, quick thought from Steve Jobs. No relationship to me. Not all Steves are related. Simple can be harder than complex. You have to work hard to get your thinking clean to make it simple. But it's worth it in the end. Because once you get there, you can move mountains. And I will say, it feels like math is complicated. Because there's all these rules and subcases and other cases. But actually, I think math is really beautiful. Because if you can get to the understanding that underlying almost all the math that you're going to do are a handful of simple ideas. And once you master them, everything else becomes fun. And it takes time. It can be hard to get there. But keep going. Now our goal for today is solving quadratic equations. And I will emphasize the word equation here. Up to now, technically we've been working with expressions, which is just manipulating what things are. So equations mean that we have the equal sign. Equals. Okay, so the goal is a little bit different. It's not just about manipulation. It's about solving. And we're going to talk about two ways to do it. You can factor. Turns out if you can factor the product of two things and get 0, you simplify the problem. You can cut it into two smaller problems. So factoring is a great tool to solving. That's why we talk about factoring. And the other thing is that there's a formula called the quadratic formula. It's one of the few formulas that a lot of people know. I've heard that there's even various songs. I'm not very good at them, but this is one of the ones that you just basically memorize. And okay. So let's get into this. Again, we have our quadratic equation. We need the equal sign. And the punchline here is it's anything which you can rewrite as ax squared plus bx plus c equals 0. We want to make sure there's a quadratic, so the coefficient of the x squared can't be 0. And we don't want anything higher than x squared. All right. And as I mentioned already, we're moving from manipulation to solving. Solving means I want to know which x's do what I want them to do. For which x, when I plug it into that left-hand side, that ax squared plus bx plus c, will I get 0 out? So we're after specific numbers. Okay. So there's questions here. Which of the following are quadratic equations? And we have a bunch of them. So let's talk about them. 3x squared plus 4 equals 7x. Quadratic equation or no? Someone said yes. Why is this a quadratic? There's no 0. Because it can be, right? Can be. We can move the 7x across. We have the technology. So since we can write this as 3x squared minus 7x plus 4 equals 0, then yes. And essentially what we're doing is we're saying, as long as we do the same thing to both sides, we still get equality. So what we're doing is we're subtracting 7x from both sides. 3 minus 2x plus x squared equals 0. Is this a quadratic? Yes. Now, what's throwing us off? Well, we're writing in a different order. But hey, you're allowed to rewrite things, so we can change the order that we add. So this is good to go. 4 minus 5x equals 2. Is this a quadratic equation? No. What's missing? Yeah, the quadratic part. t squared plus 2t plus 1 equals 0. Is this a quadratic? Yes. Now here, don't be caught up by that we introduce t's. We can change symbols. Techniques don't change. And the ideas don't change. 3x squared plus 4x minus 2 equals x squared plus x plus 5. Is this a quadratic? Yes. What can you do? Yeah, just move everything to one side. Life is good. X cubed plus 4x plus 2 equals 0. Is this a quadratic equation? I think I heard someone say no. What's wrong with this one? The cube. It's not, it says the highest power is degree 3. No, we don't want degree 3. There's ways to solve them, but we don't want to learn them. Oh my gosh, what a headache. Okay. U to the fourth plus 6 equals 5u squared. Is this a quadratic equation? As written, no. We'll say meh. Because as written, no. But what can you do? If you think of this as, could be written as u squared squared plus 5u squared plus 6 equals 0. And then you could just come up with a new name. Y plus 5y plus 6 equals 0. Sorry, y squared plus 5y plus 6 equals 0. So there's sort of there's kind of a hidden quadratic here. And sometimes they'll do that to us. One thing I probably should have written down, but I didn't write down. I'll go ahead and write this one down. Suppose I say the following: 3x squared plus 7. Is this a quadratic equation because I don't have an x term? Is it still a quadratic equation? This is not a quadratic equation. Ha, I tricked you. It is a what?
Oh, I have a question about a different one.
Oh, okay. I'll finish my mwahaha. This is a quadratic expression. Why is it not a quadratic equation? Yeah, you need to have an equal sign. So you need an equal sign if you're talking quadratic equation. You had a question.
So for the one that's
Meh.
if that shows up, should we just solve it all the way, or should we just leave it and say, like, no?
I would probably say meh. As long as you have a strong argument that, hey, this wasn't a quadratic. You're like, oh, I guess you're right. There's a strong argument to be made here. And I will say for exams, I think even for quizzes, you can appeal. If you're like, hey, Pearson doesn't know stuff. And we're like, you're right, Pearson doesn't know stuff. I'm sorry. For any Pearson representatives listening to this, you are great people. We love you. All right. So, how do you solve quadratic equations? Well, we've talked about two methods, so let's talk about method one. Factoring. So, what's the idea? We go back to this fun thing we'd mentioned. 0 has this really cool property, and it's unique to 0. And it's this property that says if two things multiply and the outcome is 0, one of the two things had to be 0. So how do we use that? Well, if we start with the quadratic and we can factor, then what happens is it says, hey, if I can factor, so I have some expressions. I threw in some Greek letters here because, math always traces back to the Greeks. Alpha x and beta and gamma x plus delta, one of these two had to be 0. So you say, it reduces down to smaller, simpler problems. Now you might say, well, how do you know these are simpler problems? Because you just say, well, how many x's do you see? Originally, there's a bunch of x's, right? Multiple x's. The more x's you see, the harder the problem. So it's, let's make a smaller problem. So factoring allows us to say, instead of saying the big thing equals 0, the individual small things equal 0, and then life is good. Okay. So we'll do some examples here. solve 3x squared minus 18x plus 15 equals 0 by factoring. Well, what can we do? Is there anything we can do? So think our game plan. We're probably going to factor because it tells us to factor. That's a pretty good clue. It's a great clue even. Is there anything we can do to start making things simpler? Sorry, what? Divide by 3. Why not? Everything has a factor of 3. X squared minus 6x plus 5 equals 0. So essentially what's happening is we're pulling out a 3. X squared minus 6x plus 5 equals 0. We say, one of these things had to be 0, but it wasn't the 3. So it must mean that this part still is 0. Okay. That seems like a simpler problem. I like that strategy. Make things simpler. X squared minus 6x plus 5 equals 0. Does this factor? Spoiler alert, it does. How does it factor? And there's lots of ways to learn to factor. There's ways we talked about. But any way that you know how to factor, that's great. So for me, I focus on, I need two things that multiply to 5, but add to negative 6. Can you think of two numbers that multiply to positive 5, but add to negative 6? Negative 1 and negative 5. So I claim negative 1, x minus 1, and negative 5, x minus 5. Now, let's check it out. You can always double check, right? X squared, good. Minus 5x minus x does give minus 6x. And minus 1 times minus 5 gives plus 5. All right, now, channeling our philosophy, hey, we have a product here. Now we're going to split it into two pieces. So you have an x minus 1 piece and an x minus 5 piece. One of those two things had to be 0. So we say, okay, so either x minus 1 equals 0 or x minus 5 equals 0. It's not that they both have to be 0, but one of them had to be 0. Okay, now we have, instead of one big equation, two small equations, but they're a little bit more straightforward. If x minus 1 equals 0, what can we say the value of x is? We can add 1 to both sides. That cancels the minus 1, and so we get x equals 1. Or, if x minus 5 equals 0, what can we say x is? 5. So this has two possible solutions. Now for quadratics, we'll talk about this in a second, you can have either two solutions or one solution. More particularly, if we want to be keeping it real, you can have two real solutions, one real solution, or no real solutions. But we'll get to that in a minute. Okay, any questions on that one? All right. Solve y squared equals 2y by factoring. What do we need to do? How do we begin?
Move the 2y.
Okay, we could move the 2y across. So in other words, let's rewrite it in our standard way. So we put the y squared minus 2y equals 0. Does y squared minus 2y factor? Is there anything here that we can do? We can take out a y. They're common. Y times y minus 2 equals 0. So again, we have a product. And we say, you know, this idea is so nice, we can just keep using it. So you have a y, and you have a y minus 2 being multiplied together. So we say, okay, that tells us that either y equals 0 or y minus 2 equals 0, right? Those are our two pieces that we're multiplying. But if y equals 0, then what is y? Ah, yes, it feels like Steve's asking a trick question. If y equals 0, then what is y? It's 0. Or, if y minus 2 equals 0, what is y? Positive 2. You know, you can add 2 to both sides. Now, I did want to point one thing out. Something that I have seen people do in the past. But not you, because you're the good students. But I just want to point this out as you help your friends. Y squared equals 2y. There's a temptation to say, hey, everything has a factor of y. Just like before we said everything has a factor of 3. Since everything has a factor of y, why don't we divide by y? And we get y equals 2. And we say, aha, that's the answer. Because we divided and it reduced down to an equation, and y equals 2, life is good. I've seen people do that. Are these the same answers? No. This says there's 2 solutions. This is only finding one solution. What happened? Why did we lose a solution by dividing by y? And what was fundamentally flawed in this approach?
You forget about the y equals 0.
Okay, it does trace back to y equals 0. So how did we lose the y equals 0 solution? So why is it we could divide by 3 and be like, oh, that's so cool. But here we're like, divide by y, ugh, we lost solutions. Ugh, that's not cool, man. Not cool. All right. The problem is, we can't, what's the one thing you're not allowed to divide by? 0. And so the problem is, dividing by y is a possible divide by 0, because y could be 0. We don't know that. And so you have to be careful. So if you're ever dividing out to cancel stuff, make sure whatever you're dividing by can't be 0. As long as it can't be 0, life is good. So 3 can't be 0, it's 3. So we can divide by that all day long. But y could be 0, so we shouldn't divide by it. So instead of dividing, move things across and factor out. So that's why we ended up with the wrong answer. So anyways, I just want to make that note. All right, the other approach, method 2, the quadratic formula. And this has been known for thousands of years. There's not a lot of things in math that we can say thousands of years ago. So if ax squared plus bx plus c equals 0, then x is negative b plus or minus the square root b squared minus 4ac all over 2a. I think that there's a couple of songs to help remember. I think one goes to like Pop Goes Weasel. X is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. You don't have to remember that. But if it helps, whatever helps. It's just one of those things you memorize. Now, you might say, aha, there's a quadratic formula. Are there other formulas? What if I had an x cubed? Yes, there is a formula. If this is the size of the quadratic formula, the size of the one with the cubic would take up about maybe half a page. Is there one for fourth? Yes, it would take up 4 or 5 pages. Is there 1/4? No. Hopeless. Impossible. Impossible. But you only need to know quadratic. That's just a fun side note. Okay, a couple of notes. You have a square root term. And so whenever you have a square root term, you get a little bit nervous about what's inside the square root term. If what's inside the square root term is negative, no real solutions, because you can't take the square roots of negative numbers and stay real. The goal in our class, we're going to be trying to keep it real. So if b squared minus 4ac is negative, no real solutions. If b squared minus 4ac is 0, then that says you have the square root of 0, which means this part goes away, and you really have a single solution, negative b over 2a. It turns out what's happening there is that really tells you that your original thing that you were trying to factor was a perfect square. So it looked like x plus b over 2a quantity squared. Now, if b squared minus 4ac is positive, we do get two real solutions. If it's a nice positive number, in other words, it's a perfect square, then we can get something that factors nicely. But even if it's not nice numbers, we could still, in principle, factor. It'll just be messy. So every quadratic, in principle, factors as you factor out the a, and then we call these different solutions the roots. So x minus the first root, x minus the second root, and we say there are two of them because of the plus minus. All right, so we'll talk in a minute about where this comes from, because I like to think of, math shouldn't be a collection of black boxes. But solve 6x squared plus 7x equals 20 using the quadratic formula. All right, so if we want to solve 6x squared plus 7x equals 20 using the quadratic formula, what's the first step we should do? Yeah, set it equal to 0. We want it to look like this expression so that we can identify the a, b, and c. So you have the 6x squared plus 7x minus 20 equals 0. So we bring things across by subtracting them over. And at this point we can say, aha, we see a, b, and c. And the negatives are part of it. So c isn't 20, c is negative 20. All right, well, we just write this down. So x equals negative b, negative 7, plus or minus, square root, b squared, 7 squared, minus 4 times 6 times negative 20, all over 2 times 6. So once you write it in the right form, figure out your coefficients and just plug them into the formula. And now the rest of it is, well, let's see if we can clean it up a little bit. So a lot of the work will be on the inside here. 7 squared, 49. Now I see a minus, and there's a second minus, so that becomes a plus. 4 times 6 times 20, what do we do? Yes, we pull out our calculators, because they're allowed, and it says 480. You say, cool, thank you, calculator. You're the best. I ever told you that, calculator? You're awesome. Calculators, they appreciate you. All right, 49 plus 480. What does that become? Yeah, ask your calculator, 529. You're like, 529. But what do we do? When in doubt, ask your calculator. And you say, okay, calculator, square root of 529. What will your calculator tell you? It might tell you a long string of digits, but in this case, it tells you 23. So again, I'm not asking you to I expect you to come up with these numbers. Use technology if you're allowed to use it, and you are. And now we're like, oh, cool. So this becomes two possibilities, negative 7 plus 23 over 12, or negative 7 minus 23 over 12. Negative 7 plus 23 over 12, what does that turn out to be? Negative 7 plus 23, also known as, or 23 subtract 7 if you like, 16. Minus 7 minus 23, so it's just a negative. Think about 7 plus 23. 30. 16 over 12, they both have factors of 4, that becomes 4/3. 30 over 12, they both have factors of 6, this becomes negative 5/2. So you get your solutions are 4/3 and negative 5/2. And there you go. Now you could use this to actually say, aha, these are nice answers, so we could factor. And I see we're out of time, so next time we'll start about why the quadratic formula works. And we'll stop here. All right, have a great day. See you next time.